Hello and welcome back to another Physical Sciences 3 lecture. In the last lecture we looked at radioisotopes, and now we're going to look at one of the types of nuclear radiation called alpha radiation. So, alpha particles are the very stable helium-4 nuclei 4-2He. They have a 2 plus charge, okay, a 2 plus charge. Because they have 2, you can imagine a helium. Normally if we drew a helium plus, oops, it's not very nice. Let me make that bigger. So I'm just drawing a nucleus. So it's a plus, and then a neutron, then another neutron, then a plus. Okay. So this would be helium. Remember we drew this before when I was looking at our. That's like a helium atom with a net charge of 0. Charge equals 0. And then the nucleus is just bang. It's just 2 protons, so helium nucleus. Without the electrons, it's got a 2 plus charge. Okay, so that's why it's got a 2 plus charge. So we just don't have those electrons balancing out our electrical charge of the nucleus. All right. So radium, so they have a 2 plus charge. Alpha emitters occur in isotopes of elements with mass numbers above 209. So they have to have pretty big mass numbers for them to be alpha emitters. And if we have a sample of radium-226, it happens to be an alpha emitter, which means that from that radium nucleus, a helium nucleus splits off. So 2 protons and 2 neutrons split off, and it forms the new element radon. So if you know that something's an alpha emitter, let's go to our periodic table. So where is that one? What are we looking for? It's quite a blood one, isn't it? Taking me a while. This is embarrassing. Why am I looking for so long? There's radon. Radium. I don't know why that took me so long. I forgot what number it's. Okay, so we've got radium, and see it splits off, so we lose 2 protons, which means the new element is 2 places down the periodic table. Radon is down here. Sorry that took so long. Radium, 88. So it splits off 2 protons and becomes radon, 86. Okay, so and then if you notice, we've got leftover radon and a helium nucleus, and then there's a lot of energy. So there's a lot of energy binding these two together. So if we split an atom, and you might know of the nuclear bomb, that's a famous splitting the atom, also now used in fusion reactions. But it takes a lot of energy is released if you split an atom, because there's a lot of energy binding those the nucleus together. Okay, so we end up with a lot of energy coming off here as well. The note left and right of the arrows, the totals of mass numbers, the upper numbers. So see, we got 226 plus 222 plus 4. They add up together, and so do the number of protons as well, the atomic numbers. So 88 on both sides. So 88 is here. 86 plus 2 equals 88. Okay. Cool, so you'll have problems here. There's lots of problems where you'll have to figure out what is going to be the element that is left over when we have alpha radiation. So if we start off with uranium 235 with a 92, we can easily work out that the next element is going to be 231 plus 90. Okay. 231 plus 90, and then let's have a look at what is element 90 on our periodic table. It is down here. It's thorium. Okay, thorium, and it's got 232. Perfect. Okay, thorium. Okay, good. So there we go. So that's how we work out this one. Those ones we just have to make sure they're all balanced, and you can just double check. 231 plus 4 and 90 plus 2. And you will notice though that if we look at our periodic table, thorium has a atomic mass number of 232. So what does that imply? implies that we have a different isotope of thorium after this alpha emission. So we have a different isotope. We just have one less neutron than we normally expect. Okay. So if you look at the parent nucleus here is the uranium-235. We call it parent. So that's what we start with. Then we split off the alpha particle. So that's the helium nucleus, and the daughter nucleus is the other element that is left over after we've split after the alpha particle has been emitted. So that's a couple of terminologies. Generally, alpha particles have very limited penetration through air, traveling only a few centimeters. Alpha particles travel at between 10% to 1% to 10% the speed of light. The alpha particles released from nuclear decay are the origin of all helium gas on Earth, including that used in party balloons. Okay, so that's how all alpha particles came to be. Okay, in the next video we'll look at beta radiation or beta radiation.